All right, so the next force we're going to talk about in our forces unit is tension. And I told you a little bit about tension, sort of some of the key ideas back in our Newton's laws unit when we were just learning how to draw free body diagrams. Today we're going to go a bit more in depth and we're going to learn how to solve some common tension problems. First thing to know about tension is that tension occurs within a material. Usually we talk about it as being in a rope or a string, but it can exist in anything. And it happens when that material is being pulled or stretched. Tension is something that exists everywhere within a material. So in this rope here, as it's being pulled or stretched by these two men, it's going to have tension here and here and here and here and here and here and here. Tension is almost another word for tightness in this sense. And you can imagine this rope would be tight or taut the whole way along it. It's not going to be really tight here and then kind of loose and floppy in the middle and then tight out here. It's going to be tight the whole way along. So tension exists everywhere within a material. Now the reason tension occurs is because every piece of the string pulls on the pieces beside it. That's why we can't have sort of a loose floppy part in the middle and tight parts out on the side here. And I'm going to draw a diagram in a second that will help to illustrate that point. But before I go on, I want to talk about one really important assumption that physicists make all the time when they're solving problems with ropes or strings. And that assumption is that the rope or the string has no mass. Now, this seems like a little bit of a weird assumption to make because obviously rope and string has mass. But what we find is that in many situations, the rope or the string has negligible mass, meaning it's so small we can neglect it, if we compare it to the objects it's attached to. This is why we can usually assume it's massless. So yes, this rope will have a little bit of mass, but compared to the mass of this guy and this guy, that mass here is going to be so tiny that we can pretty much ignore it. This is really similar to what we do with air resistance. Anytime anything moves on Earth or in Earth's atmosphere, there is air resistance. If it comes in contact with one air molecule, it will experience air resistance. But we know that compared to other forces that usually act on objects, air resistance is often really, really small or negligible. And so we just pretend it's zero. And we actually get really, really accurate answers despite that. Same is true here. We're going to pretend that this rope has a mass that's zero, and we're going to still be able to get really, really accurate answers. So if we make that assumption, what else can we figure out about this rope? Well, let's look at some of the forces acting on this rope. Over at these two ends of the rope, you can imagine this is sort of a free body diagram for that last tiny bit of rope, the bit of rope that's being held onto by this guy's hand. And a free body diagram for that bit of rope is going to have tension pulling it this way. Right? The rope beside it over here is attached to this last piece that he's holding onto, and it's pulling that piece this way. Meanwhile, this guy and his hands are applying a force to that last little bit of rope and pulling it to the right. Similarly over here, that last piece of rope that this guy's grabbing onto, it's feeling an applied force from the guy to the left, and it's feeling a tension force from the rest of the rope pulling it to the right. So what about the rest of the places along this rope? What do those all look like? Well, let's throw those in too. So basically what I'm saying here is at any point along this rope, you can choose to pick a little piece of rope, that piece there, that piece there, that piece there, and draw a free body diagram for any piece of this rope. And you would find it looks like this. This piece here is being pulled left by the tight rope to its left, and it's being pulled right by the tight rope to its right. And same with this piece, and same with this piece. So tension, like I said, is this force that exists everywhere within a rope. All these red arrows are tension. Now, let's look at the size of these arrows, because this is kind of the important bit I want to get to. Let's take these two arrows here, for example. So just looking at this free body diagram in the middle. If we apply Newton's second law, F equals ma, to this free body diagram, it says that the net force has to equal the mass times the acceleration. But we already said we're going to assume this rope has no mass. So if m is 0, it doesn't matter if this rope is accelerating or not, or what its acceleration is. If m is 0, the net force has to be 0 too, which means these two forces are balanced. So as long as my rope is massless and Newton's second law applies, which it always does, these two forces are the same in magnitude. I could do the same thing here to show that those are the same in magnitude, and the same thing here to show that those are the same in magnitude, etc., etc. But it could be that these two forces are the same, and these two forces are the same as each other, but that these two are actually different from these two. So let's compare this arrow to this arrow. Now what's happening here is this piece of rope is being pulled right by this piece, and this piece of rope is being pulled left by this piece. That's what these two arrows are. Now this might start to sound a little familiar. It sounds kind of like Newton's third law. Newton's third law says that every action has an equal and opposite reaction. So if this piece pulls right on this piece, then this piece has to pull left on this piece with the same magnitude, right? That's the equal part in equal and opposite. So Newton's third law tells us that these two arrows have to have the same magnitude. Newton's second law told us that these two have to have the same magnitude. And if we just apply this bit by bit along the whole rope, we eventually find that every single arrow I've drawn on this diagram has the same magnitude. Now this is a really, really important concept that lets us solve tension problems. And I'll sort of summarize it below here. This helps to illustrate why tension is the same everywhere on a rope. So all these red arrows are the same and is equal to the force at both ends. So these blue arrows, in fact, are also the same as all the red arrows. That's a really, really key idea when we're dealing with tension, and it helps us solve all sorts of tension problems. So that's really important going forward. I kind of gave that point to you a few lessons back without really going into it in depth. Now hopefully you understand in a little more detail why it is. So the next thing we're going to do is jump into some tension problems. And before we do that, I want to give you a set of 4 steps that I like to tell students to use when solving tension problems. Some students really don't like tension problems because there are 4 steps they have to do. Some students really like tension problems because, although maybe it's a lot of work, they know exactly what the steps are that they're going to have to do ahead of time. So let's go through these one by one. Now, the first time I give these to you, they won't necessarily make a lot of sense, and I won't dwell on them too much. I'll kind of leave you a bit confused, and then when we go to do our examples, it should help you understand what I mean in each of these 4 steps. So the first step I want you to do in a tension problem is draw an FBD for each object. We'll often have more than one object. Right? Up here, we had a guy on the left and a guy on the right. I would do a free body diagram for both of these guys if I was trying to solve this as a tension problem. The second step is to choose an axis of motion. And I'll clarify what this means when we get to our example. And note that this axis of motion can be curved. Again, more on this in a bit. Step 3 is to find the acceleration of the whole system. We're going to do this by using F equals ma, Newton's second law, but we're going to use it on all the objects kind of grouped together. And the final step is to find the tension in the rope or the string. And to do this, again, we're going to use F equals ma, but we're going to apply it to a single object rather than to the whole problem at once. Now, again, these steps might seem a little odd or confusing right now. Once we use them in a problem, it should be a little bit more clear. So let's jump into a problem. First example. Here are 2 carts attached by a rope, and they're being pulled to the right with a force of 40 newtons. So think of this as like some kid over here grabs this cart and exerts a force of 40 newtons on it, and the whole sort of train starts to accelerate to the right. We want to find the acceleration of the carts, and we want to find the tension in the rope. Now, tension problems, 4 steps. Always do the same 4 steps. Always do them in the order. So step 1 was draw a free body diagram for each object. So I'm going to draw a free body diagram for this cart and for this cart. So here's my 6 kilogram cart. What are some of the forces acting on it? Well, I'm going to have gravity pulling it down. I'm going to have the normal force holding it up. And there's a bit of tension here, pulling this cart to the right. Because this cart's on wheels, we can neglect friction. If the wheels were gone, this cart was just sitting on the ground sliding, yeah, there'd be a friction force over here. But as long as these are sort of nicely lubricated wheels that don't have too much mass themselves, they're pretty light, this basically means this car can move left, right, without having to fight any friction whatsoever. Okay, so I also told you, and I want you to get in this habit, once you've drawn a free body diagram, obviously you're going to label your forces. We'll do that in a second. And also, if there's any forces you can find right away, go ahead and do it. So there's my tension force. Don't know what it is right away. I'm going to find that in part B. Here's my gravity force, and yeah, I can find that right away. Fg equals m times g. The mass of this cart is 6. Little g is 9.8 because we're close to the surface of the Earth. So that's going to give me an Fg is 58.8 newtons. And that means my Fn is going to be the same. And remember, the idea here is, you guys know through experience, if you have a cart like this being pulled across the table, it's probably not going to jump into the air and accelerate towards the sky, and it's probably not going to start burrowing down through the table. So there's no acceleration in the y direction, which means the forces in the y direction must be balanced. That's how I know that Fn is the same as Fg. So let's look at this 4 kilogram cart now. Similar looking free body diagram. Gravity going down, normal going up. This applied force over here from the 40 newtons. But this guy has the rope on its other side. So the tension in the rope is actually pulling this guy to the left. If you were this cart, you'd feel the rope slowing you down, pulling you this way. Whereas if you were this cart, you'd feel the rope wanting to speed you up, pulling you this way. Okay, so there's my tension. And remember, we know that these two are the same. Because as we said on the previous page, tension is the same everywhere in a rope and is equal to the force at both ends. So this tension here and this tension here are going to be the same number, whatever that is. There's my 40 newtons. That's given to me in the problem. There's my Fg. I can calculate it right away using the mass of the cart is 4, get 39.2, and then my Fn is going to be the same. So that's my step 1, free body diagram for every object. Step 2 said to choose an axis of motion and note that it could be curved. Now, axis of motion is really just a couple of arrows that show you which directions your objects will be moving in and which way you're calling positive and which way you're calling negative. In this problem, it's pretty straightforward. These objects are going to be moving in a sort of left-right direction, probably to the right. And pretty standard would be to say right is positive and left is negative. So let's do that. That's my step 2. Here's my axis of motion, this line, and I'm calling right positive and left negative. Now, you still might be wondering about this can be curved bit. Because these carts are moving along a straight line, there's no need for them to be turning any corners. My axis of motion doesn't need to be curved. But if we do have corners involved, then our axis of motion might be curved, and that'll happen in the next example. Okay, step 3. Step 3 said to find the acceleration of the whole system by using F equals ma for all objects together. And this is really a key idea that lets us tackle problems like this. Because these two carts are tied together, I would expect them to have the same acceleration. Right? If this guy was accelerating faster than this guy, the rope would break. If this guy was accelerating faster than this guy, well, that would make no sense. How would that possibly happen if he's just being towed by this guy? So if we look at this problem, we say, you know what? Because these two are tied together, it's fair to kind of treat them as one object, and they'll have the same acceleration. That's key to step 3. In step 3, we find out what that acceleration is. So step 3, we're looking at the whole system because we're saying these guys are tied together, they're going to do the same thing. So I'm basically just treating this whole thing as one object, and I'm applying F equals ma. So what I'm going to do is I'm going to look at all the forces acting on both of these objects together, and I'm going to add them all together. Then this is going to be the mass, again, of all these objects added together, and this is the acceleration of all the objects, and they're going to have one acceleration because they're tied together. Okay, so let's dive into this. Now, first of all, before I start writing numbers down, to make my life a little easier, I already know that this FG and this normal are going to cancel out. This one's down, this one's up, they have the same magnitude, those are going to cancel. Same with this FG and this normal. One's up, one's down, both the same magnitude, those will cancel out. So to save myself some trouble, I'm not going to even bother listing those in my list of forces over here because I know they're just going to cancel out. So all I have to worry about is this FT, and this 40 newtons. So let's do that. I have a positive Ft, that's this guy here going to the right. I have a negative Ft, this guy here going left. There it is, negative Ft. And I have a positive 40. Here's my 40 going to the right. And then this guy and this guy cancel, this guy and this guy cancel, so I haven't bothered to write them down. So that's all the forces acting on the whole system added together. This is the mass of all the objects in the system added together. 6 plus 4, 6 comes from there, 4 comes from there. And this is the acceleration of my whole system. Now, if we go through and we solve this, plus Ft minus Ft, those cancel out. I'm left with 40 equals 6 plus 4 is 10 times A, as I have here. A, then if I solve for it, is going to be positive 4. And if I'm just putting that number into a calculator, positive 4 is great. If I'm reporting that number to a human being, I'm going to state it as 4 meters per second squared, right. Okay, step 4. Step 4 was to find the tension. And we're going to do it using a similar approach. We're going to use F equals ma again. But we're going to do it rather than on the whole system, including everything, on just one object. So we're going to pick an object. Usually it doesn't matter that much which object you pick. Sometimes there's a bit of a smarter choice. But in this problem, whichever one you pick, you'll actually get the exact same answer in the end. So it's kind of just a flip of the coin at this point. We're going to try using the 6 kilogram object. And that might be a smart choice because you can see the 6 kilogram object only has 3 forces acting on it, whereas the other object has 4 forces. So given the choice, I'd rather work with this one. It looks like it's going to be a little less work. Okay, so applying F equals ma to this object. Again, I know normal and gravity are going to cancel out. So all I should have for my sum of forces is just one tension force going in the positive direction. So let's write that down. Here's my one tension force going in the positive direction. That's my sum of all the forces on the 6 kilogram object. Now for mass, that's going to be 6. That's the object I'm focusing on. And for acceleration, wait, how do I know the acceleration of that object? Oh, right, I just found it. I just found the acceleration of everything. And it was all positive 4. So here I just take this positive 4 I found in step 3 and I plug it in for A over on this side. Then it becomes really easy to solve for the tension. I just go 6 times 4 is 24. And so the tension is 24 newtons. That is how tight or how taut this rope is as it's connecting these two carts while this one gets pulled to the right. Okay, so this problem is done. It said find the acceleration of the carts. We did that over here, 4 meters per second squared right. Find the tension in the rope. We did that over here, 24 newtons. Now let's look at a bit of a different problem. In this problem, we have two masses hanging from a massless string. Again, we pretty much always in this course assume that strings are massless. Over a frictionless pulley, another assumption we like to make. And they're released from rest. So this pulley is kind of like, think of this as a sort of an axle that's attached to the wall, and this is a wheel around that axle, and this wheel can very easily spin to the right or to the left. It's fixed to the wall, so it can't fall, but it can spin. And if we run a rope or a string over the pulley, then these two masses could kind of move up and down together. If one goes up, the other would go down. If one goes down, the other one would go up. So that's kind of what we're looking at in this problem here. And again, we're going to find the acceleration of the system, and we're going to find the tension in the string. So again, tension problems, 4 steps, always the same 4 steps, always in the same order. Step 1 is draw a free body diagram for each object. So I need a free body diagram for this guy and a free body diagram for that guy. There's my first free body diagram for the 6 kilogram mass. I've got gravity pulling it down and this string tension pulling it up. Now gravity we can calculate pretty quickly. Fg equals mg, I get 58.8 newtons. Now, keep in mind, this is not normal force. I think a lot of you are going to be in the habit of looking at a free body diagram like this, saying there's a down arrow and up arrow. Oh, this is probably Fg, Fn, and they're equal. It's actually Fg and Ft, because this force comes from the tension. And they're actually not equal in this case. Remember, up here we said these forces were equal because it would be silly for this cart to burrow down into the ground or shoot up into the air. Over here, however, it's quite reasonable for this object to accelerate down or up. In fact, looking at this, you can probably guess right away that this guy's going to accelerate down. So these two are not going to be equal in magnitude. I'll label that one, but I don't know what the magnitude is yet. Next object over here, my 4 kilogram mass. Let's do a free body diagram for that. There we are. Gravity down, tension up. Again, I can calculate gravity, and tension, I don't know what it is. I do know, however, that these two tensions are going to be the same. Because this is one rope, tension is the same everywhere in a rope. So that's my step 1. Now my step 2 is my axis of motion. These are a couple of arrows showing which directions the objects can move in and saying which direction is positive and negative. Now up here, that was fairly straightforward. This was a left-right problem, so I picked right positive and left negative. This problem, however, I've got this mass that can move up, down. I've got this mass that could move up, down, but they're sort of separate from each other. They're not directly over top of each other. They're offset. And actually, if I let this go long enough, this mass is going to shoot up, and it would go from up, it would bend around the pulley and then come down on the other side. So it's kind of like the direction this guy can move in is up, down, or bending over the pulley and then coming the other way. So I'm going to draw an axis of motion that represents that. This is the way things can move in this problem. They can move up, down over here, across or around the pulley, and up, down over here. And I have to pick a direction to be positive and a direction to be negative. It really doesn't matter. You can pick either side to be positive or negative, and you'll get the exact same answer in the end. What's important is you pick one and you stick with it, because these signs are going to be a little There's going to be some confusion as we go through this problem about vector directions. Having these signs written down is important. I randomly picked this side to be positive. So if this guy were to accelerate down, I would say that's in the positive direction. If this guy were to accelerate up, I would say that is in the positive direction. Okay. Step 3. F equals ma for the whole system. We're trying to find the acceleration. And you'll see now why this step 2 is so important. Without drawing this axis of motion the way we did, you would probably say these two have different accelerations, because one's going to accelerate down and the other one's going to accelerate up. Those clearly are going to be different. But by saying, wait a minute, I'm going to call this guy moving up positive and this guy moving down positive, they'll both have a positive acceleration. I can then actually say they have the same acceleration. And that makes step 3 doable. So we're finding the acceleration. We're going to use F equals ma. So adding up all the forces acting on all the whole system, I have this 58.8. It's going down. It's on the 6 kilogram block, so that's in a positive direction. I have this Ft. It's over here. It's going up, so that's in the negative direction, negative Ft. Then I have this Ft over here. It's on the right-hand side going up, so that's in the, which direction is this? Positive. Positive Ft. And then I have this Fg. This is going down on the right-hand side. Well, if I'm on the right-hand side, down is negative. There's my negative 39.2. You can see now why this positive and negative are important to have written down. What's the mass of everything all added together? 10. And there's the acceleration that I'm trying to solve for. What you're going to notice here is when you go to solve this, first of all, it looks like a lot of stuff you don't know, but this negative Ft and this positive Ft, those are going to cancel each other out. So you just get 58.8 minus 39.2 equals 10a. You solve and you get a equals positive 1.96. And again, if we're putting that in a calculator, positive 1.96 is great. If we're reporting it to a human being, 1.96 meters per second squared up for the 4 kilogram block, because for this guy, up is positive, or 1.96 meters per second squared down for the 6 kilogram block, because for this guy, positive is down because of our axis of motion. Okay, so that's the acceleration of the system. This guy's accelerating up at 1.96. This guy's accelerating down at 1.96. Or I can just say they both have an acceleration of positive 1.96 because of the way I drew my axis of motion. Step 4, find the tension in the string. Again, we're going to use F equals ma, but we're going to do it for one object. And let's just try this 6 kilogram object again. Again, if you pick the 4 kilogram object, you should still be able to do it. You'll still get the exact same answer. We're just kind of picking one at random here. So I'm going to do the 6 kilogram. So looking at my free body diagram for my 6 kilogram object, I'm going to add all the forces together. I have a 58.8. This is down, but remember, we're over on this side and we said down was positive. So this 58.8 is positive. Then I have this Ft going up, but because we're on this left side, that up is negative. So I have a negative Ft at positive 58.8. The mass of this one object that I'm focusing on is 6. And the acceleration, that's the guy I found over here. Everything has an acceleration of positive 1.96. So there's my acceleration, positive 1.96. Then I crunch through this on my calculator, and I find Ft equals 47.04 newtons. So that is our tension in the string. And again, a good exercise for you would be to repeat step 4, but rather than picking the 6 kilogram block, do it with the 4 kilogram block. And you should find you get this exact same number to the decimal place.